So today's lecture is related to TTT diagram, that is time, temperature, and transformation diagram. So if we observe the TTT diagram, then here TTT diagram stands for time, temperature, transformation diagram. It is also called as isothermal transformation diagram. If we see the definition, TTT diagram, which gives the kinetics of isothermal transformation. If we see the introduction of TTT diagram, T means time, another T is temperature, and third T becomes transformation. This is the TTT transformation diagram. It is a plot of temperature versus the logarithmic of time for a steel alloy of definite composition. Okay, so this TTT diagram is for alloy material. We know that alloy means if we take two and more than two materials together, then it is called as alloy. So in this diagram, the two different materials or more than two materials we mix together. It is used to determine when transformation begins and end for an isothermal, that is constant temperature heat treatment of previously austenized alloy. When austenite is cooled slowly to a temperature below lower critical temperature, the structure that is formed is pearlite. Okay, first stage becomes pearlite stage. As the cooling rate increases, the pearlite transformation temperature gets lower. The microstructure of the material is significantly altered as the cooling rate increases. By heat and cooling, a series of samples, the history of the austenite transformation may be recorded. TTT diagram indicates when a specific transformation starts and ends, and it also shows what is percentage of transformation of austenite at a particular temperature is achieved. Then TTT diagram, if we observe this diagram, temperature, degree Celsius versus time, then if we observe the temperatures, then up to 800 degrees Celsius temperature is available in this diagram. And if we see the time in seconds, so from 0 seconds to 10,000 seconds, this is the time diagram. Okay, so if we go beyond the 100 degrees Celsius, this is this stage here, m 90% is shown. And if we see the upper portion, this is eutectoid temperature region, this is gamma pearlite stage, then this is coarse pearlite. This transformation ends is here. This is the transformation begins. Okay, so this is the transformation begins and this is the transformation ends. Okay, this portion is gamma pearlite portion. This is the region of gamma pearlite. If we observe on the right side, this is coarse pearlite. Then here, this is fine pearlite. This is upper bainite. This is lower bainite. And here, this is the transformation begins. Okay, at this stage, transformation begins. And this is alpha plus Fe3C. Okay, alpha plus Fe3C. Then next is 50% portion is there. This is M90%, this is M50%, and this is gamma martensite portion is there. If we observe this diagram, this transformation starts. This red diagram is transformation starts, and this green diagram is related to transformation ends. This is stable austenite phase. This is unstable austenite phase. This is again unstable austenite phase. When it enters in this region on the right side of this red color line, then this becomes stable condition. On the right side of this green color graph, this is coarse pearlite, then this is fine pearlite. Okay, then next is feathery bainite, then as acicular bainite stage is there. If a feathery bainite is also present here, then this is martensite stage. This is temperature transformation curve. Then what is meant by stable austenite? In case of stable austenite, this is the different stages. This is near A1. This is up to 550. This range is 550 to 220. If we observe here, near A1, this sluggish transformation takes place, austenite to coarse perlite, and greater time for diffusion. For this process, time required is greater. The next is Bainite in feather-shaped patches, degree of undercooling high, slow rate of diffusion of carbon atoms retards the increased tendency of austenite transformation. Then this becomes austenite and this becomes the perlite. If we see the material is in austenite stage, then it is related to this shape is austenite, and if the stage changes, this becomes perlite stage. Austenite is stable at temperature above lower critical temperature, but unstable below lower critical temperature. Okay, so austenite stage comes when the temperature is above this LCT value, and if the temperature is lower than LCT, then it becomes unstable condition. Left curve indicates the start of transformation and right curve represents the finish of transformation. The area between the two curves indicates the transformation of austenite to different types of crystal structures. Austenite to perlite, then austenite to martensite, austenite to bainite transformation. These are the different phases present in this diagram. Isothermal transformation diagram shows that gamma to transformation is a rapid phase at speed of sound. Okay, we know that the speed of sound is very high, and at that speed, the conversion takes place from gamma to transformation takes place. The percentage of transformation depends on temperature only in this case. Then upper half of TTT diagram, if we observe here, the austenite perlite transformation diagram. In this case, this is the temperature versus time diagram. On the upper portion, this is lower critical temperature, and on the left side of lower critical temperature, this is austenite condition, and between this, on the right side of this red color line or this curve, this is the perlite phase. In between austenite and perlite, the middle region is austenite plus perlite stage. On the austenite phase, this is transformation begins at 100 percentage of austenite is here, and here 100% of perlite phase is there. But in middle portion, this phase is 50% transformation of austenite plus 50% perlite. So 50% transformation is there. As indicated, when it is cooled to temperature below lower critical temperature, it transforms to other crystal structures due to its unstable nature. A specific cooling rate may be chosen so that the transformation of austenite can be 50% to 100%, etc. If the cooling rate is very slow, such as annealing process, the cooling curve passes through the entire transformation area, and the end product of this cooling process becomes 100% perlite. In other words, when slow cooling is applied, all the austenite will transform to perlite. If the cooling curve passes through the middle of the transformation area, the end product is 50% austenite and 50% perlite is there, which means that at certain cooling rates, we can retain part of the austenite without transforming into perlite. So as shown in this diagram, this is the explanation of the diagram is here completely austenite phase is there, and on the right side this is completely perlite phase is there, and in between austenite and perlite phase, the middle portion is related to austenite plus perlite phase. Then lower half of TTT diagram, if we see the lower half diagram of TTT, then this is austenite, martensite and bainite transformation is there. This diagram is again temperature versus time diagram. On the left side of this curve, This is unstable austenite phase. This dotted line is related to 50% martensite transformation is there. On the right side, Bainite phase is there, and this is MF, martensite finish. Martensite start, martensite transformation stage comes, and martensite finish stage comes. Okay, so this becomes the lower half of TTT diagram. If a cooling rate is very high, the cooling curve will remain on the left hand side of the transformation start curve. In this case, all the austenite will transform to martensite. If there is no interruption in cooling, the end product will be martensite. If we observe the TTT diagram, it gives nature of transformation, that is isothermal or thermal, time independent or mix. Type of transformation, if you observe, this is reconstructive or displacive. If we see the rate of transformation, which shown in this diagram, rate of transformation, stability of phases under isothermal, that is transformation conditions, temperature or time required to start or finish transformation. Next is qualitative information about size, scale, etc. If we see the composition of steel, the carbon weight percentage is present and alloying element weight percentage is also present here. Grain size of austenite is present, then heterogeneity of austenite is present. Okay, if we consider the carbon weight percentage, as the carbon percentage increases, the A3 decreases. Similar in the case of AE3, that is austenite stabilities. So the incubation period for the austenite to pearlite increases. That is the carbon curve moves to right. However, after 0.77 weight percentage of carbon, any increase in carbon, ACM line goes up. That is austenite becomes less stable with respect to cementite precipitation. So transformation to pearlite becomes faster. Therefore, C curve moves towards left after 0.77% of carbon. And here the critical cooling rate required to prevent the diffusion. So in this way, today we see about the TTT diagram, and mainly this TTT diagram shows the different phases, that is pearlite phase is there, then bainite phase is there, okay, martensite phase is there. This type of phases we already learned. So many phases are shown in this diagram. So in this way, here we finish our lecture. Thank you.